Greetings to you, welcome to physics class. As promised in the other video, we shall be looking at atomic energy level today. We'll also be looking at photoelectric effects. So let's begin. This is week 8. And so in this video, we shall be looking at photoelectric effects, thermionic emission, and we quickly look at X-ray, but not that deeply. So the topic for today is structure of the atom. By the end of this lesson, you are supposed to explain with suitable diagrams what atomic energy levels are. Tell what makes an electron to undergo a quantum jump. Deduce the mathematical equation for a photon of light in a quantum jump and hence explain the meaning of the symbols therein. Discuss atomic spectra and hence explain line, continuous emission and absorption spectra. Deduce Einstein's general equation of photoelectric effects and hence explain the meaning of the symbols therein. Define photoelectric effects. Draw and label a photocell, and of course, we may not do calculations here today, but I will do that separately in the next video. So, what do you mean by atomic energy level? For you to really understand atomic energy level, you need to understand what we call uh, electronic configuration or ionic configuration, where you know the different shells of an atom. You draw the atom, you know that this is a nucleus, this is shell number one, shell number two, shell number three, and so on and so forth. So that knowledge is what we are actually applying here in today's topic. So what do you mean by atomic energy level? Electron in atoms are believed to be arranged around their nuclei in position known as energy levels or electron orbits or electron shells. I said that earlier. So here, energy level, electron orbits, electron shells mean the same thing. And so the electron has a negative charge and the proton in the nuclei of the atom has a positive charge. You all know of that. So for this reason, the electron is able to stay on its orbit or shell by a force of attraction. I told you unlike charges attract each other. So the negative charge on the electron and the positive charge in the nuclei of the atom makes the electron to stay on the shell of the atom without falling apart. So that is the force of attraction between it and the proton in the nuclei of the atom. So this is, you have to underline this statement. Very, very important. So each electron in a given atom possesses a specific amount of energy that is related to the distance between the electron and the nuclei. Since the electrons in an atom are restricted to individual orbits or quanta, they are said to occupy energy level. Note that electrons in the orbits closer to the nucleus have stronger energy, and it takes more energy to remove such electrons from the first energy level than to remove electrons from any other higher energy level. All electrons in the closest orbits to the nucleus are said to be in ground state or lower energy levels. Please take note of this. They are very, very important. So the energy of an electron is given mathematically as E is equals to negative 1 all over pi 1 over n squared dot r. where n is the electron's quantum number and r is the constant. The negative sign means that one must do work on an electron to remove it from the atom. The energy levels in the atom not to scale. So please, I want you to take note of this negative sign here, that one needs to do work. We shall be using this statement when we are discussing photoelectric effects and also Albert Einstein's equations of photoelectric effects. So take note of this particular section. So let's move on. So these are what we call energy levels. These are what we call energy level. Now, in the other video, we were discussing absorption spectra and also what? Emission spectra. That this is the nucleus and this is the shell. Let's call this first one N1, N2. So we said that if an atom jumps from this, undergoes a quantum jump from this particular shell, that is from a lower energy level, this shell 1, shell 2, let me add another shell here. Let's suppose you have another shell here. Very good. So if an atom jumps from this shell up to this shell, we say that the atom absorbs energy. It is jumping from a lower energy to a higher energy level. And so the electron, you see a wavy line here with an arrow telling you that the electron has really absorbed energy. So we call this absorption spectra. Now, this is lower to higher. And then sometimes you can have from higher to lower. So when an electron jumps from a higher energy level, let's look at this second diagram. Let's say from this down to this level, we say that the electron emits light. In this case, the electron loses energy. And so it emits a photon of light. A photon of light of hf, where h is a Planck's constant and f is the frequency of the photon of light emitted. And so this is this diagram from higher energy to a lower energy is what you see here. These lines means energy levels. And so this stage is called the ionization stage. And the end is equal to infinity. And this one is called the ground state or the first energy level. Here, your E, we have E subscript naught. And then where you have N2, you have it as your E1. Your E1, that is the first energy level. I mean, the ground energy level, then the first energy level, E1. And so in that order. So this is what we mean by energy level. These arrows are very different energy level. Let's call it, this is electrons is jumping from, let's say this the second shell down to the ground state. And so we can see that this nucleus, the cycle here, is the ground state. Here the electrons, they are more stable. And then this one is jumping from, let's say this one is E, this one is E what? This is E2. So this one is jumping from E2 to E0. This one is E3 to E0, E4 to E0. And then this one is from E2 to E1, E3 to E1, E4 to E1, in that order. So this is what we mean by energy level in an atom. Radiative transition. I just explained that here. This one is absorbed. This one is emitting light because it is jumping from a higher energy level to a lower energy level, so it is emitting light. I just explained that. This one is jumping from a lower energy, that is the ground state, to a higher energy, and then it is absorbing light. This is what I just explained in the other slides. And so the above are called energy levels, energy level diagrams. The energy states or level are numbered. N is equal to 1, 2, 3 up to infinity. They are called, this N, it means quantum number. 1, 2, 3 till infinity means quantum number. Electrons moving from ground state, that is E subscript naught, that is N equals to 1, I just explained that, to a higher energy or a certain state are said to absorb much energy. I say that this quantum jump of an electron from a lower to a higher or excited energy level happens when an atom is heated. This point is worth taking note of. Happens when an atom is heated or bombarded with an energetic particle. So when they ask you the question, when do quantum jump occur in an atom? Quantum jump occur in an atom when an atom is heated or bombarded with an energetic particle. So the electron possesses higher energy as long as it remains in the excited state. But because excited states are very unstable states, excited states are very unstable states. I will go back to where I belong to, just like Lucky Dube sang the song, I'm going back to my roots. So the electron will tell itself, I am going back to my roots. This state I am is highly unstable. Let me go back to that stable state I belong to. So, because the excited states are very unstable states for atoms, the electron soon jumps back to its original orbit or energy level and hence emits a photon of quantum of light by the general equation this. I really love this branch of physics. So that is that for that. Let's move on. Okay, before I move on, let me explain something here quickly. We are saying that electron will come back to their original state where they are most stable. Now, when you ice water, or the original form of water is liquid, and when there is a drop in the temperature of the environment or a thermodynamic system, let's suppose a fridge, the water will be ice. Now, take note that the water will not remain ice forever. The water will soon go back to its original state, liquid. That is exactly what happens here. So, this equation En simply means ground state, higher energy level. The N is an arbitrary symbol. Let me say a template that can fit in any higher energy level. And then the E naught stands for lower energy level, which is represented here by the ground state. And then H is the Planck's constant. Fn, that is the frequency at different energy level, N1, N2, N3, N4, up to N equals to infinity. H here is the Planck's constant, and C is the velocity of light, which is 3 exponential 8 meter per second. And then here is the wavelength of the photon of light emitted. So from the general equation above, we deduce other equations as follows. So E minus E naught simply means change in the energy. So we call that equation number 5. And so change in energy is equal to H times F subscript N equals to H times C all over the wavelengths. Equation star star. So you have change in energy. So what you have down here is that H, this is this for this, you have this here. So change in energy is equal to this is also equal to this. So you come down here, you are having this is equal to this, and then down here you have this is equal to this. That is what you have here. And then of course the what, H, we cancel out H, and then you are left with N. Fn is equal to C over N. That is what you have here. So where E subscript n is the energy in the excited state, that is n equals to infinity, and E subscript naught is the energy in the ground state, that is E, n is equals to 1. So this is what I just explained. Energy in the excited state, increasing energy of orbits. This is the nucleus of the atom, where you have the proton and the neutron. The proton and the neutron are located here, and then here is where the electron is located. So this is the first one here. This is your N1 shell, N2, N3. So here you will have your F1, F2, F3. That is F subscript 1. The frequency was carrying F subscript n. So here is your F subscript n, 1, and then here is your F subscript 2. And then here is your F subscript what? 3. That's what you have here. So jumping, now this electron, this is the quantum jump here. It is jumping from higher to lower, and hence it is emitting light. This is just a single photon of light, HF. If you have two photons, you have 2 HF, 3, you have 3 HF, and so on and so forth. Note that Note that not all quantum jumps are to the ground states or ground level. That was explained in this diagram. Not all quantum jumps are to the ground states. This is the diagram that just explained what I am about to say now. Not all quantum jumps are at the ground states. Note that not all quantum jumps are to the ground state or the ground level, because electron can also jump from one allowed higher energy level to a lower allowed energy level. Hence, the energy of each radiated photon is directly proportional to the length of its corresponding arrow, as can be seen below. Please note this down. The energy of each radiated photon is directly proportional to the length of the corresponding arrow, as can be seen below. So at the ionization energy level or state, the electron is removed from the atom totally. So this diagram is what I explained here. Where's the diagram? This is the diagram. So these ones jump from here to the ground state, and then this one from here to this state. That is what I just explained. So let's move on. Example number 1. I will not solve any question in today's video. I will prepare a video specifically for calculations. So all those equations from week 8 down to this particular week, you will use them here to solve various problems. Here they're asking you, an electron jumps from one energy level to another in an atom radiating this joules of energy. That is your E is equal to this. If the Planck's constant, the H is this, what is the wavelength of the radiation? Take C to be this. So I would like you to try these questions out. I've written the pattern here for you. You collect your data, you state the correct equation, you solve. And so I will go through your work, and when next we meet, I will be trying to correct those equations, the questions you didn't solve correctly. Want to look at atomic spectra or color and light frequency. In this section, we shall be concentrating on gas atom. The gas atom can give off light only if energy is first given to the atoms of the gas. A gas atom giving energy is said to be excited. When an electric discharge is sent through a gas in a discharge tube at a very high voltage and low pressure, The gas atom contains energy and are energized to give off light. This light, when analyzed, is seen to consist of light of one wavelength or color. This type of spectrum is called line spectrum. We are just done explaining what line spectrum is here. So, explanation, what do you mean by line spectrum? A line spectrum is a spectrum that consists of a number of well-defined lines, each having a particular frequency or wavelength or color. This was Neighbor's arguments concerning Rutherford's planetary uh, structure of the atom. He was supposing his own to be continuous spectra, while Neighbor said no, it is a line spectra. So, what is a continuous spectrum? A continuous spectrum is a spectrum. A continuous spectrum is a spectrum. Sorry, is a spectrum that consists of light of all frequencies or colors or wavelengths. In a line spectrum, take notes, only certain wavelengths of light are emitted, and these are different for different elements and components. This emission from a material is known as emission spectrum. This is the roots for what we call thermionic emission. Thermionic emission. This is where it springs from. And so the emission spectrum is a characteristic of a material, and it serves as a type of fingerprints. The real identity of the material, fingerprints or identification of the gas. So for instance, if a continuous spectrum, that is a spectrum containing all frequencies or color or wavelengths, is passed through a gas, dark lines are observed in the spectrum. These dark lines correspond to lines normally emitted by the gas. This is called absorption spectrum. The reason is that gases absorb light at the same frequency at which they also emit light. And so the dark lines you see Einstein's photoelectric effects. Albert Einstein also came up and was able to make his contribution in the study of matter. So, having discovered all these things and gone through all these studies, he came up with something that was so interesting. What was that? Let's check it out. Albert Einstein, in 1909, using a concept first put forward by Max Planck, proposed an explanation of the photoelectric effects. He proposed that light wave consists of tiny bundles or packets of energy, which he called photon or quanta. That each photon of light or electromagnetic wave has an energy hf, where h is the Planck's constant, c 0.6 exponential negative 34 joule seconds, and f is the frequency of the light. Mathematically, he states hf is equal to w plus half mv squared, where h is equal to f subscript naught. So hf is the total energy constant of a single photon of incident light. W is known as the work function, part of the energy that is used to get the electron free from the atom and away from the metal surface. Half mv squared, is the what? The remaining energy to give the liberated electron a kinetic energy. V is the velocity of the photoelectron. And m is the mass of the photoelectron. F naught is called the threshold frequency. So this is what Albert Einstein's equation is talking about. This is a metallic surface that receives radiation from the sun. It is heated. It is heated. This is nanometer. It is heated, and then the electrons gain kinetic energy here and they are emitted. They break what is called the potential barrier and they are emitted. They move with this, and this is the maximum velocity of the electrons. So they move emitting light. Take note, at this point, this metallic surface is now serving as the lower state of the energy. As the higher state of the energy. So, and this particular area, we can look at this as the nucleus, very hot. So, jumping from higher to low, it will now emit a photon of light. That is the simple explanation of photoelectric effect by Albert Einstein. So the photoelectric effect. What do you mean by photoelectric effects? Photoelectric effects is a phenomenon that explains the emission of electron when light falls on a metal surface. When light falls on metal surfaces. The emitted electrons are known as photons or photoelectrons. Leonard in 1902 discovered that the maximum kinetic energy or the maximum velocity of the emitted electrons was independent of the intensity of the incident light, but was proportional to its frequency. I want you to underline the whole of this. To underline the whole of this and reflect on this so that you get some sense. What do you mean by this statement? This is what helps you to understand what you are reading. You can read this thing 10 times to understand what this means. I want you to reflect on this. Let's move on. So, a graph of Ke maximum of electron versus frequency and versus frequency of light is given as. You can check this out on Google. You check it out. So from the above, F naught is what's known as the threshold frequency. This diagram refused to appear here. I'm sorry for that. Please check it out on Google. So for a frequency below or above the threshold frequency, electrons will not be emitted from the metal surface. For light with frequency less than threshold frequency are completely absorbed by the metal. The absorbed energy is hence used to raise the energy level of the surface electron or to overcome what I called earlier as potential barrier of the photoelectron. Just like for you to move a load from the ground, you have to overcome the frictional force first before the load is moved. So in this case, the potential barrier is serving as a frictional force in this topic. So this is the diagram of a photocell. They may ask you to draw correctly and label a photocell. So photoelectric effect is described in this diagram. The light comes here, and as they hit this metallic surface, they emit electrons. The electrons move, and then they start generating electricity. This is your voltmeter, your ammeter, your battery. This is the battery that converts the solar energy that gives it down to the inverter and then the inverter to the consumer. So note the following. The threshold frequency F naught is defined as the frequency of light which falling on the surface is just sufficient to liberate electrons without giving them any additional kinetic energy. The wave function W of a metal is defined as the minimum energy required to liberate an electron from a metal surface. So from equation number 10 above, we can rewrite equation number 9 as follows. That is, W is equal to HF naught is equation 10. You have this. you have this, you have this. Let's move on. So therefore, E is equal to HF minus HF naught. Also, E is equal to this. So this particular equation is what we call Albert Einstein's photoelectric equation. Example number 1, as I promised you earlier, I'm not going to solve any question in today's video. So I just want you to go through them, go through these questions, solve them. Now, X-rays. I want you to read on X-rays and jot down some very important points. That is how they are produced. How are X-rays produced? Their types, their characteristics, and properties, their practical application, and their hazards, and safety precaution. Learn also how to draw and label correctly the modern X-ray tube as well. Um, the reason why I didn't make notes on this is that I taught you this earlier, something about X-ray under electromagnetic waves. So combine that knowledge and also read on this X-ray to form these notes. So I also want you to help me attempt to these questions. Attempt to these questions. Go through them one by one. To this, I believe we have come to the end of today's lesson. Thank you for having your time with me. Stay safe and stay blessed. God bless you. Thank you.